All right, so now we are ready to complete the proof of the Mordell theorem, talking about heights. Remember that the strategy we had for the proof of the Mordell theorem was we were going to prove the weak Mordell theorem and then prove that an abelian group that has a notion of height and such that A mod M is finite, it is finitely generated. Okay, so let me first give you right away an example of what happens when you add points on an elliptic curve. So the key is going to be that the height on points on elliptic curves are going to be is a very naive height, which is just what is the size of the x-coordinate. The x-coordinate is a rational number, so it's what is the largest numerator and denominator in x in the x-coordinate. Okay, so that is going to be the height. But just to give you an idea of what happens when you add points on an elliptic curve. Here is the elliptic curve y squared x cubed plus 3. It has a point, 1, 2, right? 1 plus 3 is 4. Yeah, that point is there. And here's what happens when you do multiples of p. So the height of p here, we'll talk about heights in a moment, but the height here is 1. I'm just looking at the height of the x-coordinate. So the height is 1. The height of 2p, well, 2p is minus 23 over 16, comma, minus 11 over 64. So the height there is going to be 23. Okay. What happens with 3p? Oops, no comma. 3p is 1873 1521, comma, minus 130 870 59319. Okay, so now the height is 1873, and 4p is something like 2540833 over 7744, comma 4050085583 over 681472. Okay. First of all, you see that this point that started with integral coordinates, all of a sudden, when you do 2p, the coordinates are not integral anymore. And that's going to imply that, well, this point cannot be a torsion point because the coordinates are non-integral. If 2p is non-torsion, then p itself was non-torsion. But in any case, you see what happens with the height, that the height of the multiples of p is growing very quickly. And this is, in fact, what we're going to use to prove the Mordell theorem. This is just the typical case where the height of multiples of p are going to grow very fast. So we're going to use that in our favor. All right, so here is what's called the descent theorem. Not the descent as in you don't agree, the descent as you are descending. And it says the following. There's going to be two sort of ways that we're going to use the word descent in this class. And this is the first one of them. I'm not sure exactly where the word descent comes from here, but I have a clue that I'll mention in a moment. But this is just a theorem about abelian groups. So let A be an abelian group, and suppose that there is a height function which is a map from A to R, and a height function is defined by the following properties, such that it satisfies the following. A, or 1, let Q be in A. Then there is a constant C1 the constant depends on A and Q, such that for all points in A, the height of P plus Q is less or equal to twice the height of P plus C1. Okay. So that's the first property. 2, there is some M and a constant, and this one only depends on the group A, such that for all points in A, the height of M times P is at least M squared times the height of P minus C2. Okay, so that says that the height grows quadratically. Okay, for this M, you see that this, we're assuming that there is just one M where this works. This M is the one from the Mordell-Weil theorem, E mod M. So actually the theorem is going to work. If we had proved that the weak Mordell-Weil theorem is true for one M, this would still work. But we actually proved the Mordell-Weil theorem for all M. But it is, in this case, we just require that this happens for one M. In 3, for all constants C3, the set of bounded height is finite. Okay. Then if in addition you know that A mod MA with M as in 2 is finite, then A is finitely generated. Okay. So we are going to need to, today we're going to prove this, and then we're going to have to prove that there is a height function that does this. And the naive height function that I mentioned before is going to work. Okay, so let's prove this proposition. So here is the proof.
Sorry, can I ask a quick question about what we're doing before we get started? Thank you. So I realize that this is phrased in very general terms. Is the theory of sort of heights and descent, the descent procedure, like, is this something that exists outside of elliptic curves, or is this stated in a general way but designed specifically for addressing the Mordell-Weil theorem? Just because this function does seem like quite specialized for exactly the situation that we're in.
Yeah, I don't know enough about sort of like group theory that I've seen this in other contexts, but definitely this works for abelian varieties in general. So it's not just for elliptic curves. These heights are everywhere in algebraic geometry, that you can put heights on your points and talk about many things. You can do this in the up and coming field of arithmetic dynamics, where there are no elliptic curves and there are no abelian varieties, but you have points, and then you have iteration of algebraic maps on those points, and then you get more points and see what happens with the orbits. Heights also play a very important role in that area. So definitely the theory of heights has seen it's in several places, but I agree that I believe these theorems were proved specifically for our purpose first, I think, as far as I know.
Okay, thank you.
Yeah. So again, yeah, so as you say, like, there is a height with these very specific properties. the property 3 should be very natural. Property 3 is just saying that sets of bounded height are finite, and that's natural. Property number 2 is just saying that heights grow very fast. Okay, so that the height, when you do multiples of a point, the height grows very fast, and that's what we're saying in the example above. And property 1 just says that the height of, when you fix a q, it doesn't matter what p you choose. There's not weird interactions between q and some primes where the height of p plus q is very large compared to the height of 2p. Okay, or to compare to the height of p. It doesn't interact weirdly for any given point. Sort of like doesn't alter the height in weird ways. Okay, so here's the proof. So what we want to show then is that A over M is finitely generated given the 3 properties that we're assuming. Okay, so so let M be as in property 2. Okay, and assume that E mod M, oh, not E, A, is finite. Okay, so let pick representatives. Let Q1 through QR in A be representatives of the cosets of A mod MA. So representatives of the congruence classes modulo M in A. Okay, great. So here's the idea, and here's what I believe the term descent comes from, is that we are going to, giving a point P, I'm going to find a combination of Q1 through QR that is going to descend my point, that the combination of P minus this combination of Qs is going to descend to a set that is of bounded height. Okay, so for a P in A, there are some lambda 1 through lambda r integers such that P minus lambda 1 Q1 minus lambda r QR belongs to a set S of bounded height. Okay, so I'm going to be able to always just do some linear combination that is going to bring me to one set of finite of bounded height, but then sets of bounded height are finite, and therefore what we're going to see is that S plus Q1 through QR generate A. Okay, so that is the idea. We have to find some linear combination of Qs that when I add it to P, I go to some set that is of bounded height with a universal bound that doesn't depend on P. Right, so here's how you do that. First, so suppose, so let P be in A. Okay, I want to find that combination. Then, well, P is in one of the congruence classes. So P is congruent to some Q, some class, some index, I don't know which one, I1, modulo MA, right? So I can write, so what that tells me then is that P is M times P1 plus Q I1. Right? P minus Q I1 is a multiple of M. So for some P1. All right. So now continue like this. Now do the same thing for P1. then P1 is M times P2 plus the class, the representative of P1 in the class's mod M. Okay, and then P2 up to P n minus 1 will be M times Pn plus Qin. Okay, great. Now, for any j, what can I say about the height of one of these pj? The height will be less or equal to, so you see pj will be in the equation. What I'm using here is that pj oh yeah, I'm going to use property 2, which said what? The property 2 said this, right? So what I'm going to use is that the height, the height of m pj is less or equal to m squared height of pj minus c2. That was a property, correct? Yep. Okay. So then using that property, this is less or equal to 1 over m squared height of mpj plus c2. Okay. Now, using the definition of pj in terms of pj minus 1, this is equal to 1 over m squared times height of m times pj is pj minus 1 minus qi. So pj minus 1 minus qij plus c2. And now I can use part 1 of the properties. Again, what's part 1? Part 1 tells me this, that the height of one thing plus another is less or equal to twice the height of p. So using part 1, this is less or equal to 1 over m squared times twice the height of pj minus 1 plus c1 prime plus c2. And here, so again, I'm using property 1, and c1 prime, the constant that I pulled there, c1 prime is going to be the max of the constant c1 that appears in property 1 for a and minus qij for j 1 through n. Okay, so you see that in property 1, that constant depends on what is the q that you are adding to p. But since I'm only adding one of the q representatives, which is the q's are, there's only r of them, so I can compute the constant for every q, and then I have r constants and take the max of all of them. Okay, in fact, so we can remove this index here and then just write the j for 1 up to r, and then I've computed the constant, and it's always one of those constants. Okay, so now so that c1 prime and c2 do not depend on p. Okay, so I have that equation that tells me that I can relate the height of pj to the height of pj minus 1 with constant do not depend on p itself. They only depend on a. Great. So now, now start from Pn being, so I start from this equation, and we're going to work our way backwards to say something about P. So, and work backwards. Using that equality that I just proved. Remember, so we just proved that the height of Pj is less or equal to 1 over m squared height twice the height of Pj minus 1 plus C1 prime plus C2. Okay, we proved that. So now I start from the height of Pn and work backwards until you get to P itself. So if you do that, I'm not going to go through it, but what you get is, well, you see the constant here in front of the height would be 2 over m squared. So if you do that, what you get is 2 over m squared times 2 over m squared times 2 over m squared until you get to P is going to be that to the nth power times the height of P plus, and then what constants do you get in front of the C1 prime plus C2? The first one is 1 over m squared, and then you're going to get twice over m squared to m squared squared, so it's going to be to the 4th, plus 4m to the 6th, plus dot 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 2 to the n minus 1 over m to the 2n times C1 prime plus C2. Okay, so you get something like this. Okay. Now, what can we say about this sum? This seems geometric, so I can compute it. This is 1 over m squared times 1 plus 2 m squared plus 2 to the n minus 1 m to the 2n minus 2. And as I said, that is geometric. This is 1 over m squared times 2 to the n m to the 2n minus 1 over 2 over m squared minus 1, which is 1 minus 2 to the n over m to the 2n divided by m squared minus 2. If you simplify, I just multiply through by the 1 over m squared. And well, this is less than 1 over m squared minus 2. All right. But you see, like, the nice thing now is that the dependence on n has disappeared. So this and then is less than 2 over m squared to the n height of P plus C1 prime plus C2 over m squared minus 2. And for sufficiently large m, well, if m is bigger or equal to 2, not sufficiently large. If m is bigger or equal to 2, which it is, then 2 over m squared is less than 1 over 2. So this is less or equal to the height of P over 2 to the n plus, and m squared over 2 with m at least 2, that is more than 2. So we can replace that denominator by just a 2. Okay, so here I'm using the fact that m is bigger or equal to 2. Okay, here I've used the fact that it's geometric. And I can add those. All right, then for if n, now I let n be big enough in this process. If n is big enough, whatever the height of P is, over 2 to the n at some point is going to be less or equal to 1. So this is going to be, for large enough n, this is going to be less or equal to 1 plus C1 prime plus C2 over 2. And that bound did not depend on P. And P, if you trace back in that change of, in this chain, okay, if you trace back what P is in terms of Pn, P is m to the n times Pn plus the sum of j from 1 up to n of m to the j minus 1 qij. Okay, but the set of points, so now the set S of points such that the height of P is less or equal to this bound that does not depend on P is finite by 3, and therefore P or A is generated by the points Q1 through QR union those Qs that are of height, those are equal to 1 plus C1 prime plus C2 over 2. You can call that C3 if you want, and we know that that is a finite set. Therefore, A is finitely generated. Okay, there you go. All right. So we have the descent procedure. Now we have that. We know how to prove that some abelian group is finitely generated as long as we have a height function that satisfies 1, 2, and 3. So now we have to find a height function for elliptic curve that satisfies 1, 2, and 3. So let's do that. So heights on Pn and elliptic curves. So first of all, we're going to define just a height on Q. Okay, here's a height on Q. You just define it like this: if T is a rational number in lowest terms, so what that means is the GCD of P and Q is 1. Then we defined the height, capital H of T, to be the max of P and Q in absolute value, right? We actually can write a height on projective space on Pn of a number field. So here, this is a number field. As follows. So if you have now a point in projective space is given by coordinates like this, homogeneous coordinates, with the xi's in K, then the height in K of P is going to be the product over places of K of the max valuation of each one of the coordinates. Okay, so you take the absolute value that corresponds to those places, take the maximum value, and you actually raise it to the n nu, where n nu is the degree of the extension that you get when you complete K at nu over the nu at x. Okay. Right, and then but we're mostly going to just stick to Q. But so now, what is a height on an elliptic curve? So height, and this is the naive height on an elliptic curve over Q, which is relative to a given Weierstrass equation of your elliptic curve. If you change the Weierstrass equation, the height will change. Okay, so it's going to be a height that is given by the x coordinate of your elliptic curve. Later we will do heights in a bit more systematic way, but here is one such height. The height is going to be given by the height of a point is the logarithm of the height of x if p is not O, the origin, and 0 if p is the origin. Okay. Notice that we take the logarithm of the naive height on rational numbers because, as you saw in that example that I had at the beginning, the height grows really fast. In fact, the number of digits grows exponentially. So with the logarithm, the growth is linear, not linear but quadratic, like in property number 2 of heights. Okay, so the growth is going to be quadratic in the number of digits of the numerator and denominator, instead of exponentially in the number of digits. And that's why we put a log in there, just because, calm it down. Okay, you're growing too fast. So just take a log just to see the growth in a little bit more detail. Okay, so then we are ready to prove that the height, so we're going to prove the Mordell-Weil theorem over Q. Okay, so here is the Mordell. I'm going to put it in parentheses actually here. Because Mordell proved the Mordell-Weil theorem for elliptic curves over Q. Mordell proved it himself. So as we are about to just prove the theorem over Q, this is just the Mordell theorem. Here is the theorem, or the proposition that is going to complete the proof of the theorem is the following. So let E over Q be an elliptic curve given in a short Weierstrass equation, which we can always do because we're working over Q, characteristic 0. And then the following are true. Let P naught be a point on E. Then there is a constant that depends on P naught and on A and B, on the coordinates, on the coefficients of the Weierstrass equation, so that for all P on E, the height of P plus P naught is less or equal to twice the height of P plus C1. B, there is a constant C2 such that for all P and E, the height of 2P is at least 4 times the height of P minus C2, which was the second property of heights. And C, this is the second property with, we are specializing to M equals to 2 here, okay? And C, for all constant C3, the set of points of bounded height is finite. Okay. So let's prove that. All right, so I'm going to prove part A first. Let me actually, part C is going to fit right here. So I'm going to just prove part C, which is really quick. For any constant C3, notice that the points, the rational numbers of height, at most of height, capital H height C, is finite. Right? You just have, if you have a bound on the size in absolute value of the numerator and denominator, then there is only what about like c squared such rational numbers, right? Plus 0. So about c squared times 2, because you also have the negatives, so about 2 times c squared of such rational numbers. That's finite. But then for any x, there are at most 2 points x comma y on E, right? So if you give me coordinates x, then even if that was a x coordinate of an elliptic curve, of a point on the elliptic curve, there would be at most 2 of those. So the points on E such that the height is less or equal to C3 is at most twice the size of the number of rational points with height less or equal to, because of the logarithm e to the c. So in any case, this is finite as well. Okay, so that proves part C. That's definitely true, and that's just clear from the heights on the rational numbers. So let's prove part A. Let's see if I can actually lasso this part A. Okay. Oh, there you go. Okay, so I want to prove that. I don't know why it came over there. Okay, so now for the proof of A, let's prove A. First, taking C1 to be larger, so whatever constant we get, make it to be also larger than the max of the height of P0 and the height of twice P0. Okay, we may assume that P0 is not O and that P is not O or plus minus P naught. Okay, if you plug in, if P is P naught, then what this is saying is that the height of 2 P naught is less or equal to 2 times the height of P naught plus C1. But if C1 is bigger than the height of P naught, then sort of like that works out. Okay, so you just see what we're trying to prove. With that definition of C1, it just exceeds the bound and it's fine. Okay, so we might assume that P is not one of those points. And some fact that I'm not sure I've talked about this, but this is not hard to prove. Once you have a Weierstrass equation, the points always have a very particular form. So because E is given in short Weierstrass equation, P can be written as A over D squared and B over D cubed, and P naught similarly, they are going to be, it's X naught, let's write it, coordinates X naught, Y naught is going to be a naught over d naught squared over b naught over d naught cubed in lowest terms. Okay, so you can actually write every denominator of an x coordinate is a square, every denominator of a y coordinate is a cube, and you can sort of see why. You can imagine why, because of the shape of the short value form. It actually always happens to be that you can write all the points like that. Okay, then let's see what is the addition formula. The addition formula gives me a formula for the x coordinate in terms of p and p naught. So now the addition formula tells me that x of p plus p naught is y minus y naught over x minus x naught squared minus x naught. Okay, and if you expand this, this is x naught plus a x plus x naught plus 2b minus 2y y naught over x minus x naught squared. And if you expand this again in terms of, like, we know what the x and the y are and the x naught and the y naught are, this is something like a naught plus a d squared d naught squared times a d naught squared plus a naught d squared plus 2b d to the 4 d naught to the 4 minus 2b d b naught d naught over a d naught squared minus a naught d squared squared. Okay, and here remember that a naught, b naught, and d naught are fixed because p naught is fixed. Okay, and then you see that the height, now the capital H height of this rational number will be the maximum of the numerator and the denominator. But if you see what is going to be, so this is going to be the max of the absolute value of the numerator, the denominator, and this is, I claim, is less or equal to a constant times the max of, you see, if you just throw in the numerator, for example, absolute values everywhere, blow it and see what happens, you can multiply everything, and everything is going to be either a multiple of the absolute value of a squared, the absolute value of d to the 4th, or the absolute value of b times d, times things that depend on a0, b0, and d0, which are fixed, and those I'm throwing into the C1 prime. Okay, so where C1 prime does depend on a, b, a0, b0, d0. Okay, the C1 constant was allowed to depend on P naught, as you see in the statement, right? So that's fine. Okay, so I hope you believe that. If not, just try to work it out just explicitly what it is, the constant C1 prime, but that's believable. And on the other hand, the height of x, of the x coordinate of P, that is going to be the maximum of the absolute value of A and the absolute value of D squared, right? And remember that, well, the B squared, the B coordinate, or remember that P was A D squared B D cubed, right? Then B squared equals A cubed plus A D to the 4th plus B D to the 6th. So the absolute value of B is less or equal to, again, some constant that depends on A and B times the max of this root of A times the cube of D. Okay, I'm not being very explicit about those, but you can see sort of like this one, it's some constant that depends on A and B. Okay, I did that because then I can throw in, usually the absolute value of D showed up in here, and I didn't want it here. There was an absolute value of B there that I just want to write in terms of A and D everything. So I can use this new equation to write then that the height of x of p plus p naught is less or equal to C1 max of a squared times d to the fourth. And it doesn't depend any longer on b times d. If you see that b is bounded by this, then this is bounded by d to the fourth or by a squared. Okay, but this is C1 times the height of x squared. Okay, and therefore the height x of p plus p naught, which is the logarithm of this height, is going to be bounded by C1, some constant, plus twice h of xp. Okay. When I do the logarithm, I think I replaced here C1 by the log of C1, but in any case, it's just, again, a constant. Okay, and this is what we wanted to prove for part A. All right, and then part B, let's see, what was part B? Part B is similar. I'm not going to do it, but for part B, you just do a very similar trick to what I just did here, but using the duplication formula instead. Similar proof, but use duplication formula instead. Formula instead of addition, instead of the addition formula. And that proves the fact that this height, this naive height on an elliptic curve, just given the height of the x coordinate of a point, satisfies all three properties of the descent procedure, the descent theorem. And then because of the weak Mordell theorem, so now the weak Mordell theorem plus the descent theorem plus the properties of the height for elliptic curves over Q. These three things together imply the Mordell theorem, the Mordell theorem for elliptic curves over Q. Ta-da! Okay, so now we have the Mordell theorem over Q, and that's great. And the weak Mordell theorem actually gave us a bound for the rank of the elliptic curve, so that's awesome too. And what we're going to do next is we are going to talk a little bit more about torsion points, and then we'll also come back to heights and actually work out something that is what we call the canonical height, which is instead of this sort of like ad hoc height, we're going to have a height that is canonical in some sense and has better properties. It's like all these inequalities that I hate inequalities are going to become equalities, so it's going to be much nicer to work with. And then we're going to use that to be able to talk about dependence of points. I don't know if you've considered this yet, but once you have a module with 3 or 4 generators, now if I give you 2 or if I give you 3 points, you're going to have to decide, are these points linearly independent so they become a basis of some sort, or they at least generate a free module of rank 3? But for that, we need some sort of like way to check that they're linearly independent over the integers. If this was a vector space, then we know how to do it. But over the integers in a module, it is difficult. And heights, again, are going to be the key to solve that riddle, to check if points are independent of each other. But we can't check independence with these inequalities. We need a height that gives us equalities of heights to be able to do that, to check dependencies. So we'll do that in the next few lectures.